Hey guys, F Train here. Ready for another lesson. Hopefully you guys are doing awesome. Um, Apparently there's been a lot of people asking whether tomorrow's a holiday, a national holiday because of Sarah Jessica Parker's birthday. I just want to let you know that I checked with the government officials, and apparently it is not. So we will be having school tomorrow as per usual. Okay, just want to make sure everybody was aware of that. Okay, so today we are going to be talking about red giants. Okay, and you might have read the story of the Jolly Green Giant, but this is about red giants. Okay, so it's not the same. Okay, all right. So we talked about how stars are formed, and so let's just kind of recap that a little bit, right? So first of all, we start out with the giant molecular cloud. Again, we're talking cloud. We are talking, many parsecs in diameter. With enough mass to make hundreds of thousands of suns. Due to gravity, eventually it collapses. We talked about some of those mechanisms, maybe like things like shock waves, density clouds moving, in a galaxy. When that high density cloud in the galaxy moves through that cloud, it can cause areas of star formation. Then the next phase is protostar. So basically the cloud is now big enough or small enough, I should say, to be hot enough to start to glow. Again, it's not quite fuse. There's not nuclear fusion going on, but it's glowing. And then because it's spinning, it'll tend to, as it gets smaller. We know that things, when they're smaller, or when they're spinning and they get smaller, they'll spin faster. Conservation of angular momentum, and then eventually nuclear fusion will ignite. And actually, I don't know if I showed you, but there's sometimes when it starts to ignite, you see these big jets of gas going out the top and the bottom. It's pretty cool looking. And then eventually, when nuclear fusion ignites, it'll blow off that cocoon cloud of gas on the outside. The outer parts of that cloud will often form the planets and moons and things like that. So we'll learn more about that solar system formation in the future. Okay, and a star is born. All right, that star will be on the main sequence. It will, be fusing hydrogen, and that's how stars form. So today what we're going to talk about is so stars are on the main sequence. We've talked a lot about how that works. We've talked a lot about how stars on the main sequence maintain their equilibrium, pressure, temperature, thermostat, etc. But now what we'll talk about is sort of at the end of the lifetime of a star. Okay, so what will happen to our sun when it leaves the main sequence? It will eventually expand, and if you look on this thing here, you'll see before and after. It'll actually go off into what we call the red giant branch. It'll expand. It will get more luminous, and we'll talk about why that happens. Let me move that over. All right. So what question? How does a star become a red giant? And by the way, this is kind of like in scale. Here's the sun, here's the earth, and that would be a red giant. So red giants can be pretty giant, right? So why isn't the sun well mixed? And what do we mean by the sun being not well mixed? Well, I don't know if any of you guys have ever made a campfire. Probably not. You city folks probably haven't been out in the woods as much. Maybe some of you, summer camp or whatever, made a campfire. And if you don't move the wood around, what happens is that it just the fire dies. So every now and then you got to kind of stir it up so you get the wood that hasn't burned. You want to mix it in with the hot coals, and that way it keeps it warm. If you don't mix it, it will basically, you'll just get a lot of ash and things like that, right? So stars like the sun have what we call mostly radiative interiors. We talked about what that means. they are not very well mixed, because only the center of the sun, let's say maybe a certain diameter from the center of the sun is under enough pressure and a high enough temperature to um, ignite nuclear fusion, whereas the outer portions are not hot enough to have fusion going on. There's only fusion going on in the center. Okay. Now, once that inner core hydrogen is fused to helium, so in other words, only the centermost portion of the hydrogen can fuse into helium. So obviously, it'll start in the middle, and it'll kind of work its way out. Once all of that hydrogen has fused into helium, it's not hot enough to fuse helium. Okay, it has to be way, way hotter. I think the number is like 100 million Kelvin to fuse helium. All right, you can fact check me on that, but and it'll come up in our next lesson anyway. So so once it starts, so you'll have this helium. Basically, essentially, you have like a helium ash core remains. All right, so you have this core of helium, and it can no longer burn, at least for the short term. Okay, and this is what it looks like. So you have the core in the middle, radiative zone. Only that center core is hot enough to fuse. So what do you think happens to this ash core now that has stopped burning? Well, we've learned in past lessons, and maybe you can pause and try to answer that question on your own, but we've learned in past lessons that as something stops burning and the temperature cools, it will begin to contract. Okay. Now, but then as it begins to contract, it will get hotter again. Okay, and the temperature will rise. And what will happen then is that as this helium core contracts, it's going to get hot enough that sort of like the surface of the helium core can get hot enough to actually fuse the hydrogen that comes into contact with it. Okay, so you'll have just little shells of hydrogen surrounding the core, sort of one by one, beginning to fuse. And it's almost like a spreading grass fire. You'll have a fire, and then a little more grass burning, and a little more grass burning, and it'll sort of move outward like that. Now, why do the outer layers begin to expand as they start fusing hydrogen? So pause and think about that for a second. What's going to happen is as that shell fuses hydrogen, we know that the fusion produces a lot of outward pressure. Now, it can't go inward because there's, it's already solid in there. So, but the outside is just gas. So you're going to have this flood of energy pushing outward, and it will actually, kind of blow up the outer layers of the star. And so the star can increase in diameter 3 to 100. I've even read, several hundred times larger than the star originally was. Okay. Now, the question is, why does the star turn red as it expands? Well, if you think about it, we've learned that as it expands, what should happen to the temperature? Well, the temperature should cool, and we know that as things have a cooler temperature, according to Wien's law, you take 3 million divided by the temperature, and therefore the wavelength gets larger, so it becomes more redder, and eventually it'll become a red giant. So you have like so here's the sun. This is a Kepler red giant, maybe around 5,000 Kelvin. Here's a larger red giant, maybe 4,500 Kelvin. Okay, much larger. Why should a red giant become brighter? Think about that. Try not to laugh. Get it? Laugh. Hint. Remember, luminosity is flux times area. So what's happening as the star expands? Well, the surface area it's getting much larger, and as the surface area gets larger, the luminosity will increase. Now, even as the flux is decreasing, because the surface area goes by like the radius squared, the surface area increases at a faster rate than the flux decreases. Okay. Why does the core contract more and more as each new outer shell begins to fuse hydrogen? So basically, as the core turns ash, it contracts while the outer layers simultaneously expand. Okay, so each layer that fuses hydrogen makes the core even heavier and causes it to contract even more. And you can see here again on a HR diagram what's happening with the star as it moves off the main sequence into the red giant planet. So what conditions are needed for the helium ash core to ignite? Well, hotter temperatures. We mentioned that helium, in order for helium to fuse, the temperatures have to be much greater. But eventually that can happen as the helium core gets larger and larger because of these additional shells of hydrogen fusing into helium. The temperature will rise, and you can get helium fusing into carbon and oxygen in what they call the triple alpha process. Remember the other process we learned about, the proton-proton chain, the CNO process. There's also the triple alpha process, okay? So this can give a medium mass star like the sun a second lifetime. In other words, it'll give it more fuel as it fuses the helium. Okay, so it'll allow it to last a little bit longer as a red giant. And so basically that's what fuels a red giant. That's what allows a red giant to last, maybe millions of years, not billions, but millions of years. Okay. Eventually the helium will all become carbon and oxygen, and the outer hydrogen will continue to expand because this, carbon and oxygen is going to be very hot, and it's going to continue to contract. And so the outer hydrogen is going to continue to expand, and eventually it'll just expand right off of the star, and it'll leave the star, which will basically be what we call a white dwarf, and the outer part will be a planetary nebula. So for example, there's the Ring Nebula, which we talked about in a couple lessons ago. That's an example of a planetary nebula. Okay, that's gas that blew off of a red giant. Okay, Cat's Eye Nebula is similar. The Eskimo Nebula is the same. Okay, so I got a couple of videos. I'm going to post these on the Google Classroom. They're short videos, like 2 minutes each. These are the ones I would have shown you in class. So hopefully you will enjoy those, and let me know if you have any questions. Again, you just have to do the homework. That's I guess it's homework 218. I gave you until Friday to finish up the last homework sheet. Like I said, I mean, you should have done that weeks ago, but if you're still finishing that up, you can finish that up by Friday. That'd be great. All right. Talk to you guys soon. Let me know if you have any questions, and stay safe, and have a good Friday. Hopefully you will enjoy the holiday tomorrow. Oh wait, that's not a holiday. I forgot. Okay, never mind. Take care.